We're going to start off by looking at some bone cells and how bone tissue is formed. So one thing to keep in mind, you're constantly making bone tissue and getting rid of old. Just like your skin and most other tissues in your body, it's a constant regeneration. So we're going to start with osteoprogenitor cells. These are the cells that do mitosis to make new cells. Remember last chapter you learned about skin and there was the stratum basale, and that's where you do mitosis to make new cells that then migrate to the top? It's kind of the same idea in your bones. The osteoprogenitor cells are the ones that do mitosis to make new bone cells. And they are mainly found in the periosteum and endosteum. So you should be familiar with these from reading the chapter already. These are the linings. So periosteum lines and covers the outside of the bone, and then you have a cavity inside the bone, and endosteum lines and covers that cavity on the inside of the bone. So this is where you have osteoprogenitor cells. So we'll put OP for osteoprogenitor cells. When they do mitosis, the new cells that they make are osteoblast. So this one is an osteoblast. These are the cells that are responsible for building new bone matrix. And sometimes I say bone matrix, sometimes I say bone tissue. I kind of use those terms interchangeably. And the way I remember this is I always think of blast, build. So these cells will migrate to a central canal. So you have an osteoblast is going to be formed out here, and it's going to migrate here. So these tunnels in the bone are called central canals. So this is a central canal. A central canal is all these tunnels in the bone that contain blood vessels and nerves. So if you've ever broken a bone, you know that it hurts really bad. Bones aren't just empty or dry. They're full of blood and nerves. The central canals are where you have blood vessels and nerves. So the osteoblast migrates to a central canal. So let's look at it a little up close here. Your osteoblast is going to be here, and it's going to be a group of them. They form a ring. And the reason they go to the central canal is they need access to the blood. So we're going to use OB to mean osteoblast. They're going to be by the central canal. And they're going to build bone tissue. Remember in chapter 2, we talked about you are what you eat? Well, in order to build bone tissue, they have to get nutrients from the blood. So that's why they go to the central canal. And building bone tissue occurs in 2 steps. And if you remember from your pre-class assignment from reading, there's 2 components to bone matrix. There's the osteoid and the hydroxyapatite, the organic part and inorganic part. So that's the 2 steps of building bone tissue. So step 1 is to make the osteoid. So osteoid is the organic part of bone. And don't think about like grocery store organic, like if you go buy organic apples or something. In science class, organic has a different meaning. Organic molecules are the protein, lipids, carbohydrates, and nucleic acids. If a molecule is organic, it means it's one of those 4 types of molecules and it's made by a living cell. So in this case, we're going to make proteins, and they are made by the osteoblast. So that's what makes it organic. And this protein is mostly collagen. Just like in your skin, the dermis of your skin is mostly collagen, the osteoid of bone is mostly collagen. And collagen, the feature it adds to the bone is that it's slightly flexible. If you think about a tall building like the skyscrapers in the cities, on a windy day, those buildings will sway in the wind. If you've ever been up in the top of one of those buildings on a windy day, you can feel it swaying. They do that on purpose. They design the buildings to sway. If they didn't sway, they would snap. Your bones, although they are, firm, they do have a little bit of flexibility to them. And that little bit of flexibility helps prevent them from breaking. So this makes your bones slightly flexible. It's not much, but they do have a little bit of flexibility. And this slight flexibility prevents breaks. They would snap under the stress if they couldn't bend a little. So you have, let's draw this, what's going on. You have an osteoblast. So here's an osteoblast. It makes the collagen and then it secretes it. So you get this collagen like this. It makes and secretes the osteoid. So you have kind of a framework. Think of this like the 2x4s in the wall. So the osteoid is a framework. Then next is the hydroxyapatite. This is the inorganic part of bone. So inorganic is anything that is not made by a living cell and it's not a protein, carbohydrate, lipid, or nucleic acid. So it's pretty much everything else. And in this case, it's going to be calcium and phosphorus. So calcium and phosphorus are in rocks and soil. And then plants take them up with their roots, then they're in the plants. Animals eat the plants, then they're in the animal. And then when the animal dies and decomposes, they go back to being in the soil. So that's what an inorganic molecule. It doesn't change the whole time, whether it's in a rock, whether it's in a plant, whether it's in an animal, it's still calcium. It's not being made or destroyed. It's just there being cycled through the food web. So that's inorganic. So the calcium and phosphorus from the blood are going to combine and form hydroxyapatite. And this then coats that osteoid framework. Think about if you're building a house and you put up the 2x4s, that's the osteoid, then you put drywall on it. Drywall is the hydroxyapatite. So then you get like this. The hydroxyapatite coats that framework and it fills in so that then you get your solid bone matrix. And this calcium and phosphorus are very hard. So this is what makes the bones hard. And that is called compressional strength. So you can stand up, you can bear weight, you can put all your weight on your bones and they can handle it because they have this compressional strength. So the whole idea of being by the blood is because osteoid is protein. We know that protein is made of amino acids. So if this cell is going to make protein, it has to get amino acids from your blood. And remember, the way the amino acids got in your blood was that you ate protein and digested it. And then if you're going to coat this in calcium and phosphorus, those also have to come from the blood. So forming new bone tissue occurs by the central canal because that's where you have access to the blood to get the nutrients. So then we have this new tissue formed. So this fills in with our new bone matrix we just made. And notice that the cell surrounds itself with matrix. So once a cell has surrounded itself with matrix, it converts to our next type of cell here, which is an osteocyte. This is a mature bone cell. Every osteocyte used to be an osteoblast. So this used to be an osteoblast, but it finished building matrix and it surrounded itself. So it trapped itself in its own matrix that it built. And once it becomes trapped in this own matrix, that's when it converts from an osteoblast to an osteocyte. So you can kind of think of like osteoblast as a working bone cell and osteocyte as a retired bone cell. So the osteoblast is getting up, going to work every day, making bone tissue. Finally, it gets done, it retires, and then it's an osteocyte where it can just sit in the recliner and watch Wheel of Fortune all day. But really, the job of an osteocyte is that it monitors the stress on bones. And we're going to talk more about that later, about stress on bones, but that's what they do. They're monitoring how much stress you subject your bones to. So down here, all of these are your osteocytes. So they used to be osteoblast. So this is a continual, ongoing process. So you always have the new generation here by the central canal. They build bone tissue, then they convert into osteocytes and they monitor stress. Then another new generation is going to come in. So every time that happens, they get pushed further out. So here on the edge, this is your oldest. So you're always making new tissue by the central canal, and then it gets pushed out so that the oldest tissue is on the edge. You can notice also that it has these distinct rings. You can see each generation, right? Kind of like the rings in a tree. So each generation forms a distinct ring, and these rings are called concentric lamellae. So that is each ring. Another feature is that through the concentric lamellae, you have little tunnels called caniculus. So you can kind of see here all these little extensions like this. You have tunnels that connect these. So like these two are connected to each other by a tunnel, right? They're connected to their neighbors by tunnels. This allows them to pass nutrients and waste back and forth. So the blood, remember, is there at the central canal. And osteocytes are living cells. They need nutrients. They produce waste. But the ones out here at the edge have no access to the blood. So they have these tunnels that connect them, and that is what allows them to pass stuff back and forth. So the ones that are by the blood will get nutrients, and then they'll pass it through the tunnels to the ones out here further from the blood. And then waste gets passed forward to the blood. And one more word to go here is lacuna. Always makes me think of Lion King when I say that word. But this is the little hollow spot where each osteocyte lives. So if you look back here in our picture, here's our osteoblast, and it built this matrix to surround itself, but it leaves itself a little cave here where it lives. So the lacuna is kind of the little cave where the osteocyte lives. So you have an osteoblast formed from an osteoprogenitor cell. It migrates out to a central canal. So you can think of like the osteoprogenitor cells are the parents, right? So your parents give birth to you, they raise you, then you go out in the world to make your way. So that's the osteoblast. They're like 18 years old or 20 years old, and they're going out in the world to make their way and get a job and have a career. So that's what they're doing. They're the working ones. They're building bone tissue. Then they retire and become osteocytes. And as each new generation moves in, they get pushed out toward the edge. And this whole group, I'm sorry, there's one more word. This whole structure that you see here is an osteon. So an osteon is the central canal and the lamellae that surround it. And then if you look at this picture of the bone, so like for example right here, there's an osteon. There's an osteon. So you can kind of think of osteons as neighborhoods. So compact bone is composed of all these series of osteons. So this picture is just kind of putting that all together, the organization. So just kind of a summary. So here, for example, you can see here is an osteocyte. And you can see the little cave where it lives is the lacuna. These tunnels are the canicula. You can see here would be the new generation of osteoblast that are building bone tissue. Out here would be the oldest, and each ring is a lamellae. And you get groups called osteons. So there's the organization of bone. And one thing to keep in mind, what we'll talk about next, is what happens to the old tissue. If you're constantly making new tissue and pushing the old out to the edge, if you just kept doing that, your bones would just keep getting bigger and bigger. But they're not. So you do have another cell that we're going to talk about called an osteoclast that dissolves that old tissue from the edges. So we know that you have new bone tissue building in the middle, and then the old tissue gets pushed out to the edge, and that this is a continual process. You have to get rid of that old tissue at some point, or your bones are just going to keep getting bigger your whole life. So now we can look at the osteoclast. The osteoclast are the cells that dissolve old bone tissue. And they are made by fusing bone marrow cells. So you have several bone marrow cells fused together. So that you get this one big cell. So this whole thing right here is the osteoclast. And you can see it's really big. And I tend to abbreviate osteoclast as OC. So osteoblast is OB that builds bones. Osteoclast is OC that dissolves bones. And notice it has all these kind of like tentacles that hang down. It looks kind of like a jellyfish. All these tentacles here that hang down are called the ruffled border. And the purpose of this is to create more surface area. And this ruffled border secretes hydrochloric acid. And that hydrochloric acid dissolves the bone. And when you dissolve bone, the nutrients are returned to the blood. So remember the osteoblast were taking nutrients from the blood to make the bone? Well, now when the osteoclasts dissolve it, those nutrients go back to the blood. So you're recycling this bone tissue. And the one we're especially concerned with is calcium. So every time your osteoclasts dissolve your bone, they raise your blood calcium level by taking calcium from the bones and putting into your blood. So one of the main ideas here is that osteoclast increase blood calcium level. So now let's start to put some things together and kind of see a bigger, complete picture. So we know you have your bones are being remodeled. You're making new tissue, you're getting rid of old tissue. So on this side here, on the left, we have your osteoblast, which we know are what build the new tissue. They are controlled by the osteocytes. So here is our osteocyte. The osteocyte, remember, it's the retired osteoblast. Its job is to monitor the stress on your bones. Well, stress on bones comes in the form of exercise. So here's Donald Duck lifting weights. When he's lifting weights, that stresses the bone. Stress makes you stronger. So every time you stress your bones, the osteocytes detect this, so they will detect when you exercise. And they will stimulate your osteoblast to build more bone. And when they build more bone, your bones get stronger and denser. And you do this by taking calcium from your blood. So this has the effect of reducing your blood calcium. Then on the other side, we have the action of the osteoclast. Osteoclasts are controlled by hormones. So you have here in your neck the thyroid gland and the parathyroid glands. So the big part here is the thyroid gland. It's this butterfly-shaped gland in the neck. And its main job is to control your metabolism, but it also monitors your calcium. Then embedded inside of it, these little dots here, that is the parathyroid. So both of these glands monitor your blood calcium level. The thyroid gland responds if calcium is high. So if you have high blood calcium, then this gland secretes calcitonin. The parathyroid responds when blood calcium is low. Okay, so whenever blood calcium is high, the thyroid responds and secretes calcitonin. Whenever blood calcium is low, the parathyroid responds and secretes PTH. Now, I have to put an asterisk here by this, though. Calcitonin is mainly only effective in children, and we don't know why. Science has not figured this out, but we know that this only works in children. Adults are pretty much just running on PTH. Okay, so we'll go ahead and we'll look at what calcitonin and PTH do, but just keep in mind that this stuff about calcitonin applies to children. Okay, so these hormones are going to control the action of the osteoclast. So here is your osteoclast, and remember it is dissolving the bone. And raises blood calcium. Okay, if blood calcium is already high, you don't need to add more calcium to the blood. So calcitonin is going to inhibit your osteoclast. It's going to tell them, hey, take the day off. We have plenty of calcium in the blood already. We don't need you adding more. PTH has a synergistic partner. Sometimes hormones work in partners. Think of this like Batman and Robin. Right? They work together to fight crime. So PTH is going to get its synergistic partner, which is calcitriol. So if blood calcium is low, your parathyroid gland secretes PTH. PTH goes to the kidney and says, hey, come on, calcitriol, we got to go raise blood calcium. Then the two of them are like Batman and Robin, and they go out to raise blood calcium. Remember, osteoclasts are what put calcium in your blood. So they are going to stimulate the osteoclast to work more. So let's put all this together. Here is your bone. On the one hand, in response to exercise, you have osteoblast build bone tissue. This makes your bones stronger. And it reduces your blood calcium because you're taking calcium from the blood to put into the bones. On the other side, you have your osteoclast dissolve your bone. This is controlled by hormones that tell them if they should work more or work less based on what your blood calcium is. So let's look at some scenarios. Let's look at scenario one. Let's say we have somebody who, say it's break from school, like you've got a month off from school or something, and you spend that month, you just lay on the couch and watch TV, and you have a lot of Dr. Pepper and tacos. Okay, if you're laying on the couch, you're not exercising. So this means that your osteoblasts are not being stimulated to build bone tissue. And if you're eating a lot of tacos and Dr. Pepper, that's not putting calcium into your blood. That's a low calcium diet. So you're going to have low blood calcium, which is going to cause you to use PTH and calcitriol. And you're going to dissolve your bones more. So the net effect of this is that you're not building new tissue and you are dissolving your own tissue. So you are going to have a net loss of bone tissue. So your bones are going to get weaker during that month you spend laying on the couch drinking Dr. Pepper and eating tacos. Okay, let's look at what else you could do with your month. Maybe you go to the gym and you exercise. And you decide you're going to be healthy and you eat lots of yogurt and broccoli. Okay, so exercise is going to stimulate your osteoblasts to build bone. And the yogurt and broccoli is going to put plenty of calcium into your blood. So you're going to have calcium from your diet. Now, in an adult, this doesn't necessarily mean you're going to get a lot of calcitriol. What it means is that you will have it doesn't necessarily mean you'll get a lot of calcitonin. That's in children. This means you will have low PTH and calcitriol. You'll just turn down your PTH. So you will do less stimulating of your osteoclast. And the net effect of this is you're going to have a net gain in your bone tissue, or at least not lose bone tissue, depending on some other variables going on. Hormones, estrogen plays a big role in this, your age plays a big role in this, so there's other factors. But you will at least avoid making your bones weaker. Okay, so we've been talking about putting calcium in the blood. Let's look at why you need that. There are 4 main reasons why you need blood calcium. Your heart relies on calcium in order to beat. And we will cover this quite a bit in chapter 19, but in order for your heart to beat, it has to have access to calcium from your blood. Your neurons use calcium to secrete neurotransmitter. And we will learn about this in chapter 12 when we talk about neurons. But in order for your nervous system to work and secrete its neurotransmitter, it has to have access to calcium from your blood. Your muscles need calcium in order to contract. And this we will learn in chapter 10, how muscles use calcium to contract. And finally, your blood needs calcium in order to clot. Like when you get a cut and you're bleeding and you stop bleeding, that's because you made a blood clot. You have to have calcium in order to make blood clots. So again, it's kind of redundant, but just to make sure you understand the importance of this, you have to maintain homeostasis of blood calcium. So right here, 8.9 to 10.1 milligrams per deciliter. That is your homeostasis for blood calcium. That's the amount of calcium that has to be in your blood in order for your heart to beat, your neurons to secrete neurotransmitter, your muscles to contract, and your blood to clot. So calcium can only be one of 2 places. It's either in your bones or it's in your blood. If it's not in one, then it's in the other. Think of your bones as like your bank account, and think of the blood as like your wallet. Let's say every day you get up and you come to school and you want to make sure you have about $9 or $10 in your wallet. That way you can buy lunch and you can get a drink from the vending machine and you can make it through the day. So every day, if you have less than $8.9 in your wallet, then you go to the bank and you get some money out. If you find that you have more than $10.1 in your wallet, well, you don't want to walk around with all that extra money, so you go to the bank and you deposit some money in there. You're constantly going back and forth to the bank to make sure that you always have about $9 or $10 in your wallet, because that's what you need to get through the day. So that's how it is with your bones and your blood. The calcium is either in one or it's in the other. So when you have extra in your blood, you move it into your bones. If you don't have enough in your blood, you move it out of your bones. So we know that the osteoblast will build bone, and they are what move the calcium from blood to bone. So from your wallet into your savings account. And we know that the osteoclast are how you withdraw that calcium. So osteoclast dissolve bone to move calcium from bone, which is your savings account, to blood, your wallet, the calcium you're using. The main way this is controlled is through PTH. PTH is your main method of control. It's pretty much in charge of how much calcium goes back and forth between your blood and your bones. And again, this is talking about an adult. So kids would have calcitonin, but we're going to focus on what happens in adults, so we're not even going to mess with calcitonin. We're just going to talk about PTH. So if your blood calcium is low, then you will have more PTH. The lower your blood calcium, the more PTH you need. That extra PTH will stimulate your osteoclast to dissolve more bone. So your osteoclast will work harder, and they will dissolve more bone. This will then raise your blood calcium. Okay. If blood calcium is high, if you're doing good and you have plenty of calcium in your blood, then you just have less PTH. You turn down the PTH. And when you have less PTH, then you're not telling your osteoclast to work. So they get kind of lazy. They hang around, they take long breaks. They're not really doing much. So in the absence of that stimulating PTH, your osteoclast just kind of take it easy. So in an adult, that's the basics of what's going on. You just adjust your amount of PTH. If you need more calcium in the blood, you get more PTH, so you dissolve more bone. If you need less calcium in the blood, then you have less PTH, and your osteoclasts just kind of take it easy. We're going to take one final look here at maintaining blood calcium, and we're going to go into more detail about PTH and its synergistic partner, calcitriol. We're going to begin this story with vitamin D. This molecule right here is vitamin D. And there are two ways you can get vitamin D. We already talked about this in chapter 6. Remember that sunlight stimulates your skin to convert cholesterol to vitamin D. So if you notice here, there's two arrows here pointing to vitamin D. So one way that you can get vitamin D is from your skin. Your skin will convert cholesterol when you are in the sun. So UV light stimulates your skin to convert cholesterol. So there's the cholesterol that your skin's going to convert into vitamin D. The other way to get it is from your diet. So they have a picture here of a glass of milk as representative, but there are a lot of different foods that contain vitamin D. Either way, you end up with vitamin D in your blood. So if you're sitting out in the sun and your skin's making it, or if you're drinking a glass of milk or eating some other food with vitamin D, either way, you now have vitamin D in your blood. Your blood is flowing through your body and it's going to go through all your organs. As this vitamin D flows through your liver converts it to calcidiol. So this molecule is calcidiol. It used to be vitamin D. So as the vitamin D flows through your liver converts vitamin D into calcidiol. Then your blood's still flowing through your body. So now you have calcidiol in your blood, and your blood is going to flow through your kidneys. So now we have calcidiol in your kidney. Now we're going to pause there and we're going to come over to the other side of our story. Remember here, these little dots inside the thyroid are your parathyroid glands. And they monitor your blood calcium. And when blood calcium is low, they secrete PTH. So from these parathyroid glands, we're going to get PTH. The lower your blood calcium, the more PTH. The higher your blood calcium, the less PTH. So low blood calcium corresponds to more PTH. The lower your blood calcium is, the more PTH you have. Now, before I mentioned PTH has a synergistic partner, it's like Batman and Robin. PTH has to go get its synergistic partner. So PTH is going to go to the kidney. Now, we left off with calcidiol sitting there in your kidney. PTH tells your kidney to convert calcidiol to calcitriol. So over here we can put your kidney converts calcidiol to calcitriol when it is stimulated by PTH. So that's the important part here. When stimulated, we'll put by PTH. So the idea here, in order to get calcitriol, you first have to have PTH. If you don't have PTH, you'll have vitamin D, you'll have calcidiol, and that's it. You just stop there. To do that last step and get calcitriol, you have to have PTH. And the more PTH you have, the more calcidiol your kidney will convert to calcitriol. So more PTH also equals more calcitriol. So now you have PTH and calcitriol together in your blood. So this molecule here is calcitriol. So it used to be calcidiol. It gets converted to calcitriol by the kidney when the kidney is stimulated to do so by PTH. So just a review of what we have so far. You get vitamin D either by in your food or sitting in the sun. Your liver converts that to calcidiol. Then your parathyroid gland monitors your blood calcium level. When blood calcium is low, it secretes PTH. PTH tells your kidney to take that calcidiol, convert it to calcitriol. Now you have PTH and calcitriol in your blood. And the lower your blood calcium, the more PTH and calcitriol you have. So these two hormones are synergistic partners. So remember, that's like Batman and Robin. They're going to work together. And if we think about their job, remember, homeostasis is your overriding goal. Well, if their problem is that your blood calcium is low, they are going to work together to raise your blood calcium to bring you back up to homeostasis. So the bottom part here shows us the effectors. This box, and this is something this textbook does consistently, so get used to seeing a blue box at the bottom. This is our effectors. So think back to chapter 1. Remember when you first learned about homeostasis, you have a stimulus. In this case, the stimulus is the low blood calcium. You have the gland that's going to sense that. Your parathyroid gland senses it. It secretes a hormone, PTH, which gets its partner, calcitriol. Then you have the effectors, which are going to fix the problem. Your problem is low blood calcium. So here we have 3 effectors. The first one here represents osteoclast. So there's a picture of a bone, and this represents the osteoclast in your bone. So both PTH and calcitriol are going to work together to stimulate the osteoclast in your bone. You're going to make the osteoclast in your bone work more so that they will dissolve more bone, and they will put that calcium into your blood. So they will move calcium from the bone to the blood. And the effect of that is to increase your blood calcium. Then our next effector is the kidney. This one is also going to be PTH and calcitriol working together. So your kidney filters your blood. And all the gunk that it cleans out of your blood becomes urine. Urine is stuff you want to get rid of. So think about like you're cleaning out your closet and you're deciding what you want to keep and what you want to give to Goodwill. You're going through, you've got a t-shirt, and you're like, I don't know, am I going to wear this t-shirt? Should I keep it or should I give it to Goodwill? You have to decide. That's what your kidneys do. They're cleaning out your blood. And every molecule that's in your blood, your kidney has to decide, should I keep this molecule? Do we need it? Or should I put it in the urine and get rid of it? Well, you have hormones that help your kidney make that decision, right? So imagine your friend is there and your friend's saying, oh yeah, that's a really cool t-shirt. You should keep it. That's what PTH and calcitriol do. They tell your kidney to keep the calcium in the blood. They say, oh, kidney, we definitely want that calcium. Don't put it in the urine. Keep it in the blood. So as long as you have PTH and calcitriol, you're not going to lose calcium in your urine. You're going to keep it in your blood. The last one here is calcitriol alone. And this is going to come up again later. It's going to be important. Calcitriol alone stimulates your small intestine. Your small intestine is what absorbs nutrients into your blood. So you eat food, and your small intestine is what transfers the nutrients into your blood. Anything your small intestine does not put into your blood becomes feces. So let's say you eat some food that's high in calcium. That food is now in your intestine, and it's broken down into all its component nutrients. And your intestine has to decide which nutrients do I want to put in the blood. So which nutrients does the body need that I should put into the blood? And which nutrients should I just let become part of the feces? I don't want those, right? It's like going shopping. You're walking through Walmart and there's all this stuff there. You have to decide what you're going to put in your cart and buy and take home, and what you're just going to pass up and leave there in the store. That's what your intestines are doing. You eat food, you put all these nutrients in your intestines, and they have to pick through and decide what goes in the blood, what becomes feces. Well, calcitriol tells your small intestine to put the calcium in the blood. Without calcitriol, the calcium you eat would just go into the feces. You wouldn't actually get it into your blood. It would be a waste. So that's how you manage your blood calcium. And one of the important parts here, that end part with the calcitriol in the small intestine. Let's just suppose that you eat a high calcium diet. So you are putting lots of calcium into your small intestine, but you lack vitamin D. Okay, so you never go out in the sun, you don't eat foods that have vitamin D, your body's lacking vitamin D. What do you think is going to happen to all that calcium that you eat? Well, in this case, if you lack vitamin D, if there is no vitamin D, then you get no calcidiol, which then means no calcitriol. Okay, if we look back up here, calcitriol used to be calcidiol, and calcidiol used to be vitamin D. So if you take out the first step, you lose steps 2 and 3. Well, if there's no calcitriol, then there is nothing to tell your intestine to put calcium in the blood. So you would eat your high calcium food, and this food would go into your intestine. It would be broken down into all its component nutrients, and you'd have a bunch of calcium sitting there, and your intestine is picking through, deciding what to put into the blood, and there's nothing there to tell it to put the calcium in the blood. So it doesn't. It's like walking through the store and you forgot to put calcium on the shopping list, so you don't put it in your cart, you don't take it home. All that calcium you ate just gets lost in the feces. You would then become deficient in calcium also. So if you pay attention, calcium tablets, like if you go to the vitamin aisle at the store and you look at the calcium tablets, they also have vitamin D with them. If you just take the calcium by itself and you don't have any vitamin D, you won't absorb the calcium. You'll just have a bunch of calcium in your feces. The only way to get calcium into your blood is to also have vitamin D, because the vitamin D gets converted to calcidiol, which gets converted to calcitriol, which then stimulates your intestine to absorb that calcium. And this is assuming you're taking your calcium tablet every day. When you say you start taking a calcium tablet, with that first calcium tablet you take, you're going to poop out the calcium because you have to get that D into your system so that it has time to go through those conversions and become calcitriol. Then tomorrow, when you take your second calcium tablet, now you'll have the calcitriol and you'll be able to absorb the calcium. But that's the link between calcium and vitamin D. Now we're going to look at the epiphyseal plate and how children grow. This picture is an up close of the epiphyseal plate if you looked at it under a microscope. I'm going to start off by giving you some context. We say here's a typical bone. The epiphyseal plate, you have two of them, one here and one here. So this picture is here. And the one on bottom would be this picture, but flipped upside down. And the epiphyseal plate is hyaline cartilage. And this is only in children. Adults don't have an epiphyseal plate. And the way it works is the cartilage grows outward. So the cartilage on the top is going to grow this way. The one on the bottom is going to grow this way. The cartilage grows outwards. And as it does, the bottom part gets converted to bone. So you have a plate of cartilage at each end. That cartilage grows, and as it grows, the old cartilage gets converted to bone. So the bones grow outward from the center, and that's how the bones get longer, and that's how children grow taller. So now let's go back and look at the epiphyseal plate in detail. It is divided into zones. So we're going to start at the top and we're going to work our way down. Up here, we have zone 1. This is the zone of resting cartilage. This cartilage is not growing. Its job is just to attach the epiphysis. So you have here is the epiphysis. It's that end knobby part of the bone. Notice it's on the other side of the epiphyseal plate from the rest of the bone. So the zone of resting cartilage just serves as a joint to attach the epiphysis to the rest of the bone. Then we can move down here to zone 2. This is the zone of proliferation. This means you're doing mitosis and making new cells. And cartilage cells are called chondrocytes. So this is where you have mitosis of your chondrocytes, so that you get more cells. And as you make these new cells, they stack to form columns. So you can see, like, here is a column of cells. Here's a column of cells. Right? All those purple things there are the cells that you're making by mitosis, and they form these columns. The blue in between is protein matrix. So we have this actual photograph. I'm going to make a diagram down here under it just to kind of go along with what's going on. So we have zone 2. You have all these cells. So we'll make the cells a different color here. You have all these cells. And you're doing mitosis and you're making new chondrocytes, and they form these columns. Then between them, you have all this protein. So the blue is the protein matrix between the cells. So kind of similar to bone. Remember how the osteoblasts secrete that protein matrix? That's what's going on here too. Okay. Then we can move on to zone 3. Zone 3 is hypertrophy. This means that the cells get bigger. And as they grow bigger, the cells within a column connect to each other. So here are our columns. And notice you can see the cells are bigger and they're touching each other. So if we look at zone 3, and notice that because now the cells are touching each other, the protein that was separating them is dissolved. So you dissolve the protein that is within a column. So down here with zone 3, our cells have grown taller. So they're kind of like this, and they're touching. And as they grow together and touch, they dissolve the protein within them, but you still have the protein here on the sides. So now you have a column of cells that are touching, and you have protein on each side of that column of cells. Zone 4 is calcification. Calcium is going to come in and coat that protein matrix between the columns. And the cells are going to die. So in zone 4, I'm not going to draw the cells now because the cells die, but you still have that protein. And now you have calcium coating it. So we can put, this can kind of be our calcium coating on the protein. And where the cells were is an empty tunnel. So the cells die and they leave an empty tunnel. Then we go into zone 5 is ossification. This means we're going to convert the cartilage to bone. So you have an empty tunnel. Remember in bones, we had central canals. It was an empty tunnel and then a blood vessel and a nerve were in there. That's what's going to happen here. In zone 5, we have our protein and it is coated in calcium. And now we're going to have blood vessels and nerves move into this tunnel. Well, once you have an empty tunnel with blood vessels and nerves in it, that is a central canal. Now think about what you've already learned about bone formation. you have a central canal. Now osteoblasts are going to come and move in around this central canal. And osteoblasts are what build bone tissue. And now what was cartilage is turning into bone. So here, with your growth, that would be happening right here. So if we labeled our zones here, like zone 1 would be up here, and this would be zone 5 down here. And on the bottom, it's just the opposite. This would be zone 1, and this would be zone 5. Same thing, just upside down. And so your bones are growing outward from the center as the cartilage grows, and then the cartilage gets converted to bone. So that's the basic process of how the bones grow. Now let's look at how this is controlled. The epiphyseal plate is controlled by hormones. Now, adults are not growing, so everything we're saying here applies to kids. And we're going to divide this into 2 stages of life, pre-puberty and during puberty. So on the left here, we have pre-puberty. So this is like from the time you're born until you're 12 or whatever, when puberty starts. So we have children here. In children, their growth is controlled by growth hormone. And we're going to focus in just on 3 zones of the epiphyseal plate. In zones 2 and 3, so in 2 and 3 is where cartilage grows. Right? You're making more cartilage cells, those cells are getting bigger. So zones 2 and 3 is the part where the cartilage is growing. Zone 5 is the part where you convert that cartilage to bone. So we can kind of summarize this down to 2 basic processes. In zones 2 and 3, cartilage grows. In zone 5, you convert cartilage to bone. Growth hormone stimulates both processes, and it stimulates them equally. So if we do, for example, if we say in zones 2 and 3 where the cartilage grows, let's say a child adds 3 centimeters there. And I'm just making up pretend numbers just to make the point. Then you have zone 5 where you convert that cartilage to bone. It would be 3 centimeters. Let's say the next year the kid has another growth spurt and we add 5 centimeters of cartilage. Well, then you would convert 5 centimeters to bone. It's always going to be equal. Growth hormone stimulates both processes equally. So in a child, the epiphyseal plate stays the same size. Right? Because if it grows 3 centimeters, you add 3 centimeters to it, but then you convert 3 centimeters to bone, so you lose 3 centimeters. So really it's just staying the same size, but the kid is growing and getting taller. Okay, then we go to puberty. And puberty, we have to split up between boys and girls because they have different hormones. So in the boy, you're going to have testosterone. And in the girl, it's going to be estrogen. So both of these hormones are going to stimulate zone 5 more than zone 3. So let's look at the boy first. Testosterone has a slightly stronger effect on zone 5 than zones 2 and 3. So let's make up just some pretend numbers. Let's say that you have 2 and 3, the cartilage grows. And we're going to have zone 5, where we convert to bone. Let's say that the boy has 3 centimeters of cartilage growth. Well, then let's make just simple basic numbers. Let's say 4 centimeters as converted to bone. Let's say then he has 5 centimeters of cartilage growth. Well, let's say 6 centimeters is converted to bone. So there's a slight loss of epiphyseal plate. If you gain 3 but lose 4, you come out -1. If you gain 5 but lose 6, you come out -1. So as a teenage boy is growing, the epiphyseal plate is shrinking. Okay, let's look at the girl now. Estrogen has a much stronger effect on 5 than 2 and 3. So if we do our same scenario here, you have 2 and 3, the cartilage grows. You have 5, the bone is converted. Just to make up simple numbers, to keep it easy, let's say the girl has 3 centimeters of cartilage growth. Well, then let's say she has 5 centimeters of conversion to bone. Let's say she has 5 centimeters of cartilage growth, and then maybe 8 centimeters converted to bone. When a girl goes through puberty, the epiphyseal plate quickly shrinks. So if we look at what's going on during puberty, you get growth spurts, but with those growth spurts, you lose epiphyseal plate. Eventually, you run out of epiphyseal plate. And once that happens, you can't get any taller. You now have an epiphyseal line, which is just a little scar where your epiphyseal plate used to be. So children have epiphyseal plates, adults have epiphyseal lines. There is a difference between a plate and a line. You can't use those terms interchangeably. And once you have an epiphyseal line, your bones can't grow anymore. That's it. You will not get any taller. And just to clarify, we've been talking about like osteoblast and how they build bone tissue. That is making your bones more dense. So there's a difference between making your bones more dense and making the bones longer. The epiphyseal plate is what makes the bones longer. That process stops at the end of puberty. Throughout your life, you can exercise and stimulate your osteoblast and make your bones more dense. Okay, if we go back and we think a little bit about growth and getting taller. On average, adult men are 5'9". That is the average height for an adult man. And an adult woman, on average, is 5'4". So there is a difference between height in men and women. And if you think about kids and growing up, if you think about junior high, let's just kind of go through the lifespan here. We first of all think about pre-puberty. Pre-puberty, there's no difference in growth between boys and girls. They have the same growth. Then during puberty, like if you think about junior high, usually in junior high, girls are taller. This is because girls start puberty younger. But then by the time you graduate high school, usually the boys are taller. Because the boys start puberty later, they get more years with growth hormone than the girls do. So boys are already taller when puberty starts. Growth hormone kind of lays the foundation for your height. So before puberty, you're growing with growth hormone, you're maintaining your epiphyseal plate, that's laying the foundation. Then once puberty starts, you're growing with sex hormones, and you're building on that foundation that growth hormone gave you. The more years you have with growth hormone, the bigger your foundation is. So there is a correlation between the later you start puberty, the taller you end up being. And kids who start puberty young end up being shorter as adults because they have less years with growth hormone to lay that foundation for their height. And because girls tend to start puberty at a younger age than boys, is why in junior high, the girls are usually taller because they've started puberty at junior high and they're having that growth spurt. The boys typically have not started puberty yet and they haven't hit that sex hormone growth spurt yet, but their growth hormone is having more years to lay that bigger foundation. Another difference is when the epiphyseal plate closes. So remember we said that with boys, the epiphyseal plate shrinks slowly. With girls, it shrinks quickly. So with girls, usually by the age of 18, that epiphyseal plate is completely closed up. And it's usually earlier. 18 is about the latest. Most girls are done growing by about 15 or 16 years old. There's always exceptions. These are just in general. But in general, most girls are done growing by age 16. It's very rare to have a girl grow after the age of 18. Because in boys, that plate shrinks slowly, they can have more years of growing in puberty. For boys, they can still grow up to age 25. Now that's the outside range. Not all boys will grow in their 20s, but it is possible for men in their early 20s to still grow taller. And here's an example of this. If you watch basketball, you may know Dennis Rodman. He played for the Detroit Pistons, then he went and played for the Bulls with Michael Jordan. He's one example. Scottie Pippen is another famous person who's an example, but here's a little video about Dennis Rodman and his growth spurt.
Dennis Rodman didn't even make the high school basketball team. He actually graduated at 5'6". I mean, he played basketball, but he was never on track to make it to the NBA. He had never played organized basketball. I mean, he played pickup, stuff like that. So at 5'6", he's not making it into the NBA. The only guy at that high or lower is Muggsy Bogues, and I don't think Dennis Rodman had refined skills like that. Not at all. So he gets a job as an airport janitor. An airport janitor, okay? Obviously, doesn't look like he's going to the NBA at this point, but he goes from 5'6" to 5'9" between the ages of 18 and 20. So now he's normal height, but really not on track to go to the NBA. But then at the age of 20, he jumps up from 5'9" to 6'7". That is 10 whole inches. That's almost a foot. And obviously, now he's getting a little bit noticed. People see him in the airport asking him what college he goes to. So, I mean, he's not going to a college. So he ends up going to a community college, North Central Texas, and does his thing there. Good enough to go to a small school in southeastern Oklahoma State where he averages 26 points and 13 rebounds and eventually gets drafted in the 1986 draft in the second round by the Detroit Pistons. And the second he stepped foot in the NBA, he never proved himself to be an elite scorer. That was never the case. I mean, in his second season was his career high in points.
So the rest of the video goes on to talk about his basketball career. But the point was the height. When he graduated high school, he was 3 inches below the average height. And it wasn't until his 20s that then he grew to be well above average height and had a very successful career in the NBA. So just to show, the point of that is that it is possible for men to keep growing until age 25. They can have those like growth spurts because of how testosterone slowly closes that epiphyseal plate. So let's go back now and visit that idea of the calcitriol, and we're going to expand on that idea a bit. So you've seen this picture before. Remember, this is where you have vitamin D, which you can either get from your diet or your skin can make it when you're in the sun. It goes to your liver, which converts it to calcidiol. Then from your liver, it goes to your kidney, and in the presence of PTH, your kidney will convert the calcidiol to calcitriol. Then remember, calcitriol is what stimulates your small intestine to absorb the calcium you eat. So the point here is, like I said before, you have to have vitamin D in order to absorb calcium. So what happens if you don't have enough vitamin D? You get a disease called rickets. And here is a picture of rickets. Rickets causes bow-legged. So the legs you can see are unnaturally bent. That's because the bones are soft due to a lack of calcium, and the weight of supporting the body makes the bones bend. So the steps, now it doesn't necessarily mean you aren't eating enough calcium. The steps in getting rickets is you lack vitamin D. So if you lack vitamin D, then there's no calcitriol. And if there's no calcitriol, then your intestine can't absorb calcium. And if your intestine can't absorb calcium, then you don't have the calcium to put into your bones. So this is kind of an old-fashioned disease. It used to be common in the 1800s. In the 1900s, it all but went away. But now it's kind of making a comeback. So if we look a little bit at history and see what's going on with this. In the 1800s, rickets was common. All right, so if you think you have it tough today, at least you didn't live in the 1800s when your parents would have sent you to work in a factory or a coal mine. Today you have to be 16 to get a job. That law came about in the 1930s. Before that, your parents could send you out to work. So in the 1800s was the Industrial Revolution. This is when we started to have factories and coal mines. And those were staffed in large part by children. So during this time, kids worked in factories and mines. Going to school was a luxury for these kids. Well, there's no sunshine in factories and mines. So since the kids were not being exposed to sun, their skin was not making vitamin D. Also, with the Industrial Revolution is when we got cities. So before the Industrial Revolution, over 90% of people were farmers. And if you lived on a farm, you had a cow and you had milk and you had vegetables and all your food right there. Well, with the Industrial Revolution and factories, you started to get cities. So you had cities, but there wasn't yet refrigerators or semi-trucks, things like that bring food into cities. So you had city living, but no good fresh foods. Or I shouldn't say no at all, but definitely a lack. Today, you can live in the city and you can have access to plenty of good fresh food because we have semi-trucks to drive it there and you have refrigerators to put it in to keep it good. Well, in the 1800s, neither of those existed yet. There was no way to have good fresh food in the city. So these kids had poor diets. So the combination of poor diet and of being in a factory or a coal mine all day away from sunshine made a lot of kids vitamin deficient. And so a lot of them got rickets. So in the 1800s, rickets was pretty common. Then in the 1900s, few things happened from when we got the child labor law. So we stopped sending kids to work in factories and coal mines. So now kids were not cramped up in these buildings or underground all day and they could get sunshine. We also started to get new inventions, refrigerators, transportation, a better way to get food into the cities. So their diet improved. And rickets pretty much disappeared. Nobody was getting rickets anymore. Well, the reason rickets is in your textbook now in the 21st century is because it is making a comeback. Rickets rates are rising. So can you think about why rickets rates are rising? Why are kids today starting to get rickets again? Well, we have technology. Kids want to sit and play on their phones. Rather than outside running around playing, they're playing on their phones. So kids choose to spend their time inside on technology. And we have lots of junk food. Kids would rather have a Pepsi than a glass of milk. So the combination of choosing junk food And choosing to be inside and play on technology is once again making kids vitamin D deficient and causing rickets.